Hello everyone. Here we are going to start with the model 4, the lecture 1. So in the model 3 we discuss about the different type of modulations there. Then in the model 5 we'll be going to see the different the, the signal, how it is going to spread throughout the spectrum. So in between those things, the application and the modulation, so between we have a one path which is called as a channel. So we are going to see how the transmission will be going on through this band limited channel. So the channel is like a limited to some kind of a set of frequency. So it has to be done within that thing. So that's my suggestion. It's like to carry out within those the frequency has to be passed on to the limit of the frequency. So first we'll have some brief introduction about what is all about the terms. Okay, so we usually consider the digital communication over a additive white Gaussian noise that we usually consider AWGN channel as, and evaluated the probability of the error performance of the optimum receiver for several different type of modulation techniques. So we had discussed more about the noise which we used to consider was the additive white Gaussian noise, that AWGN, and also some performance level has to be considered of the optimum receivers, like what we did in the detection of the thing, the probability of error we found for different BPSK, BFSK, and QPSK also, and also we did it for the non-coherent types like FSK and DPSK also. So we had derived the derivations and to know the what is the error performance there. For some we didn't do. So we consider that the noise was not related to the additive white Gaussian noise. Now here we are going to see what other the noises we are going to consider. So here in this model we treat the digital communication over a channel that is modeled as the linear filter with a bandwidth limitation. So we model something that is like a limited to some bandwidth. Okay, and that bandwidth channels are mostly encoded in the practice, like for example in the telephone channel, micro line of sights, radio channel, the satellite channel, and underwater acoustic channel. The underwater acoustic is like a sonar what we use. The telephone channel is like the bandwidth which is provided for the 100 users, 10 users, and only that much users can be used. We cannot go more than that users. Then the microwave line of sight is all the for radio channels. The bandwidth which has been allotted, it will be for some certain distance. If you go across that limit, for example when you are hearing FM9, if you cross some certain let of the regions there, we cannot have a sound of all those things. The satellite channels, very good example is our the DTH and all. It's so the frequency has been selected in that we have selected one channel to our DTH. Like that we have the certain we have limited there out of bandwidth which is provided in that one small bandwidth is allotted to our use there, but it might be in different terms of a telephone, microwave, anything like radio channels or satellites, like what we use it for DTH and all. And then when we go for underwater, it's like very good example is a sonar there. We'll also see that a linear filter channel distorts the transmitted signal. Yeah, we can see the filters also might some kind of add noise to it also. Instead of filtering other things, some light noises can be added to it. The channel distortion results in intersymbol interference that we call as the intersymbol interference. What is this intersymbol interference? Okay, for example, this is the bandwidth of a signal, and this is my signal. The 3-bit has to be transmitted. Okay, this 3-bit has to be transmitted, but it's the channel length is all about the small, but it has to transmit this one. This is the pass what we has to pass, and this 3-bit has to be passed through it. So what is happening here? The channel size is small, it is limited to some certain thing, and this 3-bit is a little more than the channel size here. So what will happen here? So this is one very the crucial about it. Okay, this is one very crucial about it. Um, what we can say is like, for example, one door is there. You can make two people aram se can be passed like the horizontal way. But if a third person will come, they have to other two person has to tilt 45-degree left or right while passing through it. That's you can see when the people are very rush in the bus and all that adjust in such a thing. The people are so that is we call as a making the ways for two persons, but it is adjusted in such a way that three pieces are formed, so that we don't see a comfortness. When you're standing two people, capability is only two people are standing, that we call as a comfortness. So that this is the signal. So what is this happening when we are sending this three signal up to that equivalent? So what will happen? So some part of the signal will be merged here of this for second signal with the first, and also the for second signal with the third signal, and we make it such a way that it is passed through this length, passed through this one. So this is what we call as the inter-symbol interference. The symbol of the second one is interfering with the first one, the third one is the symbol interfering with the second one, so it is compressed and we are sending, so that we call as a inter-symbol interference. I'm telling in terms of a it's a general way. Okay, so this is what it is happening, and it is what will cause this the interference is what is causing the probability of the error at the detector part is in increase. So some of the devices have been used correcting or undoing this just kind of a channel distortion we call as a the channel equalizers. So this part we'll be looking at the end of this one, end last video. Okay, what we have a complete a video related to the channel equalizer. So different type of a channel equalizer, how to correct all these factors. Now the we just in brief we see what is this how the transmission occurs to the band limited channel. So a band limited channel such as a telephone wire line is characterized as a linear filter with the impulse response of a C of t, and the frequency response of C of t is nothing but C of f, where C of f is equals to the integrated from minus infinity to plus infinity the C of t into e raised to minus j2 pi ft dt. This is what we call as the equation 1. Okay, this is what the general channel impulse response, what it is going to add with the input signal. The input signal, what is when it is passed through the channel, this will get multiplied. What you say, the impulse response will be added to that feature. If a channel is a baseband channel that is limited to BC hertz, so this is some bandwidth what is going to happen, then C of f is equals to 0 for mod of f greater than FBC. So this is the frequency what it is going to design. The C of f is equals to 0 for if the frequency is greater than the what is the channel design. For example, if a bandwidth is designed for BC, if again more than the BC is there, it will become 0. The C of f will be equal to 0. So that is what is say. Any frequency component at the input to the channel that are higher than BC hertz will not be able to pass by the channel. Now we consider the design of signal. We consider the design of signal for transmission through the channel. So this transmission through the channel that are band limited to W is equals to BC hertz. So we are designing all anything is to BC hertz. The bandwidth is set to the BC hertz. Henceforth, W will denote the bandwidth limitation of the signal and the channel. So signal whatever we sending, it should be within BC hertz. That is equal to the what W we have set. The frequency is set to those things and made to pass through it. Okay, and made to pass through it. Then whatever the channel we have set it to that thing, and signal has also to be set so signal has also to be done with respect to those things. Now if the input to a band limited channel is a signal waveform gt of t, where the subscript T denotes the signal waveform is output of the transmitter, or the output of the transmitter. Then the response of the channel is the convolution of GT of T with the C of T. That is what is now what is the input is it is represented in terms of the GT of T, the impulse, where the T is substituted that it is the output of the transmitter. GT of T is nothing but the band limited signal. The input what is given is with respect to the GT of T, and it is going to is going to multiply with the channel signal. Thus that is we represent in terms of the convolution. When you take a convolution of GT of T with the C of T with the input signal with respect to the channel, and this input is what after the transmitter. So whatever the process has to be done, it has done. Then it has to given to the channel, and in the channel the impulse response of this will be convoluted here. That is now h of t, that is after channel what it is going to get is equal to minus infinity to plus infinity c of tau into gt of t minus tau d tau. So we can represent this one as the c of t convoluted to gt of t. If you represent this one in the frequency domain, h of f is equals to c of f into gt of f3, where gt of f is the spectrum, or we can say the Fourier transform of this signal gt of t, and h of f is the spectrum of h of t. Thus the channel alters or distorts the transmitted signal gt of t. So if anything, the modification has to be done. So for example, in noise everything is again added, it will be modified with respect to gt of t. So the visually what we say, it has like the h of f is what the convolution factors of the channel and also the signal. Now let us assume that the signal at the output of the channel is corrupted by a AWGN. After we are getting from the output of the channel, which giving it to the receiver, so that time another some signal has been corrupted by the AWGN. So that time the signal at the input to the new modulator is of the form h of t plus n of t, where n of t denotes the additive white Gaussian noise. So now you can see here, this is what the frequency here. Within this one, it is going to add here. If anything frequency more than this, it's not going to add. And this is the phase response, how it is the particularly. It is perpendicular and it is linear up till this bandwidth. You can see it here. It's like a linear up to certain thing. This certainty is what? This is nothing but the value of this W, and here this is nothing but, so how the bandwidth is there. For example, how this picture, it is again more. For example, it is little, the waveform is little more here, the bandwidth was provided, it will take again little more here, and it will start to bend here. So this is what the concept here. Okay, now so now the linear channel filter, what is the model, is shown below, how it is done here. Okay, this is what the signal what we are giving gt of t is passed on to the linear filter channel, then h of t, that is what the output of the channel, then it is when you giving to the receiver, it will be get added by the h of t with the n of t. So that is r of t is equals to h of t plus n of t. Okay, so this is what it is going to add. Now it is be coming to the receiver part. Now let us pass the receiver, the received signal r of t is equals to h of t plus n of t through a filter that has a frequency response. So now I am getting the frequency response. gr of f is equals to h convoluted h of f e minus is to the power of minus j2 pi f t naught. Okay, h historic sign there, so it is telling that the response what is got after the that which is going to the receiver filter, where T naught represents the nominal delay at which the some sample the filter output, and R denotes that the match filter is at the receiver. The signal component at the output of the match filter at the sampling instant t is equals to T naught is Ys of T naught is equals to the integrated from minus infinity to plus infinity h of the modulus the whole square df is equals to E of h, epsilon of h we said. So what is that? This we are getting the magnitude, the output of the match filter which has been matched here. So I want only the magnitude at what which is going to see. So I am getting the only this thing. So that you can be related to the epsilon of it, right? Which is the energy in the channel output waveform h of t. The noise component at the output of the match filter has a zero mean. So we don't have any mean, and I have a spectral density, power spectral density of Sn of f is equals to n0 by 2 into h of the whole square. It's the mod of the h of the whole square. It is. So the noise component we got, and we got the signal component. Okay, so this is what we require, and we related to EH here. So now noise power at the output of the match filter has a variance sigma n the whole square is equals to integrated from minus infinity to plus infinity Sn of f df is equals to n0 by 2 integrated from minus infinity to plus infinity h of the mod h of the whole square df is equals to n0 epsilon h divided by 2, n0 epsilon h divided by 2. So we related this one because we have derived it in the previous one. So n0 by 2 is nothing but EH by 2. So then the SNR, the signal to noise ratio, the output of the match filter is S by N at the output is equals to E square H divided by N naught EH divided by 2. So now that is equals to 2 EH, or we can say epsilon also. So epsilon H divided by 2. So what is this equation represents? That it is an expression for the SNR at the output of the match filter. Okay, so what we had derived it here, we are just asked to pass through the signal through the transmitter, then it is passed to the channel, and that is what we have got it to the receiver. So here we are using the linear filter at that receiver, sorry, at the transmitter first, then the channel, and then the receiver. So we are going to see with the characteristic how it is going to act in the transmitter, receiver, channel, and the receiver. So we are using the linear filter, which is a band limited thing. So after this we are going to check with the how it is going to react, and we are checking with the after passing through this all these components, and after all the processing we are going to check with the how it is going to act with respect to the signal to noise ratio. And we can determine the EH is been more, so more EH will be increased. If EH is increased, again it is multiplied by 2, so it is can say the noise will be reduced there. So now if the signal strength is increased, the noise component will be more, so that time we can say it as the signal to noise ratio will be dependent more on this component, the signal component there. So we can have a very much high performed signals there. Thank you.